this circuit shows a 2-input TTL NAND gate. Transistor Q1 having 2 emitters, and these 2 emitters behaves as PN diodes. So these 2 diodes or 2 emitters with 4 kilo ohm resistance behaves as 2-input AND gate. A and B are 2 inputs. So if we have 2 emitters, we can get 2-input NAND gate. If we have 3 emitters, we can get 3-input NAND gate. Each emitter behaves as PN diode, and with this 4 kilo ohm resistance and plus 5 volt supply voltage, it behaves as AND gate. Transistor Q2, this is used for the purpose of inversion, and transistors Q3 and Q4 form totem pole connection. If Q3 is on, Q4 is off, and if Q4 is on, then Q3 is off. When Q3 is on and Q4 is off, we find high output Y at collector of transistor Q4, and when Q3 is off and Q4 is on, then we get low output Y at the collector of Q4, and this is the truth table for this circuit, which is the truth table of 2-input NAND gate. If in transistor Q1 we have only 1 emitter, then this circuit behaves as a NOT gate or inverter. When Q1 has only 1 emitter, there is only 1 input, and if that input is low, we get high output Y, and if that input is high, we get low output Y. So if only 1 emitter for transistor Q1, this circuit behaves as NOT gate. Now we see how TTL circuit is formed for NOR gates. The basic NAND gate design is modified to obtain NOR gate of above figure. This is the NOR gate, TTL NOR gate, 2-input NOR gate. The basic design of TTL NAND gate is slightly modified now. Now we have two inputs A and B, and these two inputs A and B are separately given to emitters of two transistors Q1 and Q5. Q5 and Q6, two transistors are additional in the basic design of TTL NAND gate to form this TTL NOR gate. Transistors Q1, Q2, Q3, Q4 are the same as in the basic NAND gate design. Transistors Q5 and Q6 have been added to produce O-ring. Transistors Q5 and Q6. These two transistors are added in the basic NAND gate design. These two transistors are used for the purpose of O-ring or operation. Transistors Q2 and Q6 are connected in parallel to produce O-ring followed by inversion to get no-ring. Transistors Q2 and Q6 are connected in parallel, and this will produce OR operation O-ring followed by inversion followed by NOT gate. So OR gate plus NOT gate, this circuit behaves as NOR gate. It behaves as two input NOR gate. Similarly, we can produce TTL circuits for AND and OR gates. To get circuit for AND gate, we will use circuit of NAND gate, and an additional common emitter transistor is added before the totem pole output, which produce an additional inversion, and NAND gate followed by inversion is equal to AND gate. Similarly, to get OR gate, we will use circuit of NOR gate, and in the circuit of NOR gate we will use an common emitter transistor which is used for inversion before totem pole output, and NOR gate with this inversion that is equal to NOT gate is becomes OR gate. So to produce AND function, another common emitter transistor stage is inserted before the totem pole output of the basic NAND gate design. The extra inversion converts the NAND gate into AND gate. Similarly, another common emitter transistor stage is inserted before the totem pole output of the NOR gate design. The extra inversion converts the NOR gate into OR gate. In this way, by adding common emitter transistor to the basic design of NAND gate, we can form AND gate, and by adding this common emitter to basic design of NOR gate, we can find OR gate. Buffer drivers. Buffer or drivers. A buffer is a device that isolates two other devices. Typically, a buffer has a high input impedance and a low output impedance. In terms of digital ICs, this means a low input current and a high output current. Since the output current of a standard TTL gate can be 10 times the input current, it can be used as a buffer. When manufacturer optimizes the design for maximum output current, this device is called a buffer or driver. Encoders and decoders. A number of TTL chips are available for encoding and decoding data. The 74147 is a decimal to BCD encoder. BCD means binary coded decimal. It has the 74147 is a decimal to BCD encoder. It has 10 input lines for decimal numbers and 4 output lines for BCD numbers, binary coded decimal numbers. The 74154 is a 1 of 16 decoder. It has 4 input lines for a binary number and 16 output lines for hexadecimal numbers. 7 segment decoders 7446, 7447, etc. These 7 segment decoders are useful for decimal displays. They convert a BCD nibble into an output that can drive a 7 segment display. Following figure illustrates the idea behind a 7 segment LED display. It has 7 separate LEDs that allow us to display any digit between 0 to 9. These are 7 LED light emitting diodes: A, B, C, D, E, F, G. These are 7 LEDs and these can be used to display any number between 0 to 9. For example, number 7 is displayed when LEDs A, B and C are on, as shown in this figure. Seven segment displays can also be used to display hexadecimal digits. This can be used to display hexadecimal digits. In hexadecimal digits, we have these decimal numbers from 0 up to 9 and then A, B, C, D, E, F, 6 more digits. Digits A, C, E and F are displayed in uppercase in capital letters, while digits B and D are displayed in lowercase. B and D, two digits are displayed in lowercase. If these are displayed in uppercase, then they will be same as some decimal numbers. Digit B, if displayed in capital letter, then it will be displayed like number 8, and digit D, if it is displayed in capital letters, then it will displayed like number 0. So these two digits B and D are displayed in lowercase form. Schmitt triggers. When digital signals like that of figure A, this is some digital signal shown in figure A, and this figure shows vertical transitions between 0 and 1 state. High value represent value 1 and low value represent value 0, and the transitions between 0 to 1 or 1 to 0 are vertical transitions. When digital signals like that of figure A are transmitted and later received, they are often corrupted by noise, attenuation, or other factors, and may wind up looking like the ragged waveform of figure B. So there may be distortion in this waveform, and we get a waveform like that of figure B, in which the transitions from 0 to 1 or 1 to 0 state are not vertical, and this may be due to noise, attenuation, or some other factors. Schmitt trigger is a TTL circuit that is designed to clean up ragged looking pulses, producing almost vertical transitions between the low and high state and vice versa. This is shown in figure C. The waveform of figure B is fed into this circuit Schmitt trigger, and output from this is shown here, and it shows vertical transitions between 0 to 1 or 1 to 0 state. The 7414 is a Higgs-Schmitt trigger inverter. Higgs inverter means there are 6 inverters. So there are 6 inverters, and Higgs-Schmitt trigger inverters, 6 Schmitt trigger inverters in one pack. The 7413 is a dual 4 input NAND Schmitt trigger. 2 Schmitt triggers gates like figure B. This is 4 input NAND Schmitt trigger. Hysteresis symbol inside each inverter designates the Schmitt trigger function. There are 6 inverters or 6 NOT gates, and a hysteresis symbol is formed inside the symbol of these 6 NOT gates. This hysteresis symbol represents Schmitt trigger function. And or invert gates. Figure A shows AND OR circuit. This is figure A. There are two AND gate which produces output as AB and CD, and these outputs AB and CD are input to the OR gate, and output from the OR gate is Y. So this output of OR gate Y will be equal to AB plus CD. So this is AND OR circuit. AB and CD are outputs from two AND gates, and OR operation of these two will produce output Y equal to AB plus CD, and this circuit is known as AND OR circuit. The gate that is easy to derive and comes close to having an expression like equation 1, that is Y equal to AB plus CD, is the AND OR invert gate shown in figure C. Figure A shows AND OR gate. Output Y is AB plus CD. Figure B is same. It also produces Y equal to AB plus CD. There are 4 bubbles formed as shown in this figure. 2 bubbles. Each bubble represents NOT gate, NOT operation. 2 bubbles continuously will cancel each out. So figure A and B are same, and figure A and B are same, and figure C shows output Y equal to AB plus CD bar. A bubble is formed at OR gate. So output of this circuit will give Y equal to AB plus CD bar, and this is known as AND OR invert gate. If output Y is AB plus CD, then gate is known as AND OR gate, and if an extra inversion is produced, then output Y will be equal to AB plus CD bar. So this is known as AND OR invert gate. This is TTL circuit for AND OR invert gate. There are 4 inputs, AB and CD. 2 emitters of transistor Q1 with 4 kilo ohm resistance behaves as AND gate, so it will produce an output AB. Similarly, 2 inputs CD are applied to another transistor Q5. These 2 emitters of transistor Q5 with 4 kilo ohm resistance behaves as another 2 input AND gate, and this AND gate will produce output equal to CD. Next, 2 transistors Q2 and Q6 are connected in parallel, and this parallel combination produce ORing followed by an inversion. So output of this TTL circuit Y will be equal to AB plus CD bar. That is the output of AND or invert gate. Next we see multiplexers. What are multiplexers? Multiplex means many into one. A multiplexer is a circuit with many inputs but only one output. By applying control signals, we can steer any input to the output. 16 to 1 multiplexer or data selector. Following figure shows a 16 to 1 multiplexer, also called the data selector. The input data bits are D0 to D15. These are 16 input bits. Only one of these is transmitted to the output. This is the circuit. There are 16 input bits from D0 to D15. D0, D1, D2, D3 up to D15. These are 16 input bits. Only one of these is transmitted to the output. Control word ABCD determines which data bit is passed to the output. This is the control word ABCD having 4 bits, and these 4 bits are also connected with NOT gates. So we have 8 lines, control lines. 4 are for ABCD and 4 are for A bar, B bar, C bar and D bar. This control word ABCD control and determine what will be the output of this circuit Y. Only one of these 16 input bits will be transmitted from this circuit and obtained at this output Y. If this control word ABCD is 0000, all these 4 bits A, B, C and D are 0, then we see the upper AND gate is enabled but all other AND gates are disabled. Therefore, data bit D0 is transmitted to the output giving Y equal to D0. Here there are 16 AND gates. If control word ABCD is 0000, the upper AND gate having 4 inputs, and these 4 inputs are A bar, B bar, C bar, D bar. And if A, B, C, D each is 0000, then A bar, B bar, C bar, D bar are 1111. Each of the 4 inputs is 1. So output of uppermost AND gate will be 1, and from this OR gate we get output Y equal to D0. Each AND gate have 5 inputs. 4 are from these 8 lines A, B, C, D and A bar, B bar, C bar, D bar, and 5th line is from one of these 16 input bits from D0 to D15. So upper AND gate have 5 inputs. 4 are A bar, B bar, C bar, D bar, and fifth is D0. So if A, B, C, D each is 0, that is input control word is 0, 0, 0, 0. Output Y will be equal to D1, D0. Similarly, if the control word is changed to A, B, C, D equal to 1, 1, 1, 1, this is equivalent to decimal number 16. So the word obtained at the output Y will be equal to D15. So there are 16 combinations of this input word A, B, C, D from 0, 0, 0, 0 to 1, 1, 1, 1. And from these 16 combinations, we find output Y as one of this input bit, either D0 or D1 or D2 or D3 up to D15. If ABCD is 0, 0, 0, 0, output Y is D0, and at last if input control word ABCD is 1, 1, 1, 1, output Y will be equal to this last bit D15. Boolean function generator. Multiplexers give us a simple way to transform a truth table into an equivalent logic circuit. For this purpose, a 16 to 1 multiplexer or data selector is used, in which input data bits are equal to the desired output bits of the truth table. For example, if we have this truth table, this is truth table for 4 inputs A, B, C and D. So we have 16 such combinations. If there are 4 inputs, we have 2 to the power 4, that is 16 combinations. If we have 3 inputs A, B, C, then we will have 2 to the power 3, 8 combinations. If we have 2 inputs only A and B, then we have 2 to the power 2, that is 4 combinations. So if we have 4 inputs A, B, C, D, we have 16 such combinations from 0, 0, 0, 0 to 1, 1, 1, 1. And this is the output Y, which may be any one of the output Y may be 0 or 1. Multiplexers give us a simple way to transform a truth table into an equivalent logic circuit. If this is a truth table and we want to find a logic circuit which produces this truth table, then this is done by using multiplexers. For this purpose, a 16 to 1 multiplexer is used, in which input data bits are equal to the desired output bits of the truth table. This is 16 to 1 multiplexer or data selector. It have 16 input bits, and these input bits are same as those shown in this truth table as Y, output of this truth table. So 16 to 1 multiplexer or data selector have 16 input bits, and these 16 input bits are same as output of a truth table. Following figure shows the use of a 16 to 1 multiplexer to generate a Boolean function. And we have these A, B, C, D, which are 4 inputs of this truth table, and then output of this multiplexer will be the same as according to this truth table. So a 16 to 1 data selector can be used as a logic circuit which produce a truth table like this. Universal logic circuit. This 74150 is a 16 to 1 multiplexer. This TTL device is a universal logic circuit because we can use it to get the hardware equivalent to any four variable truth table. Word multiplexer or nibble multiplexer. This figure illustrates a word multiplexer. There are two words. On left we have a word, 4-bit word L3, L2, L1, L0. L is for left. And in right we have another 4-bit word, that is R3, R2, R1 and R0. And a control signal that is termed here as write is used, and we use a NOT gate which produces invert of this write. If write is 0, then this NOT gate will produce 1, and if write is 1, then this NOT gate will produce 0. This control word write is connected to the 4 NAND gates at right side, and this inverted write control bit followed by NOT gate, and this output of NOT gate will connected to these 4 NAND gates at left. The outputs of 4 NAND gates of write are connected to these 4 inverted OR gates, and output of these left NAND gate will connected to the inputs of these inverted OR gates. And we can see that if write is low, then we get this output OUT as L3, L2, L1, L0. That is the word at left. So when write is low, we get the left word L3, L2, L1, L0 as OUT, and when write is high, we get this output word OUT as write word, that is R3, R2, R1, R0. So this figure work as a word multiplexer. We can find in the output as either left word or right word. To find right word in this output, we have to put this control bit right as 1, and to produce output as left word, we have to put this control bit right as low. So if right is 1 high, then right side word is obtained, and if control bit right is low, then left side word is produced. This type of circuit is known as word multiplexer or nibble multiplexer. These two words are two nibbles, left word and right word, L3, L2, L1, L0, or R3, R2, R1, R0. These are two nibbles. Nibbles means string of 4 bits. So this is word multiplexer or nibble multiplexer.